Hope you guys find yourself well today. Today is the 6th of April 2020. Last time we talked a little bit about how interference could produce beats, which is going to cause kind of the increase and decrease in the amplitude of the sound due to constructive and destructive interference. Today we're going to look at interference in a slightly different way. We're going to look at how interference can create standing waves that are fixed on strings that are both ends. And a lot of instruments, whether it's a guitar, a cello, a violin, a bass, even a piano, kind of employ this idea in order to create the different frequencies that you hear. So let's see what we mean by that. So I'm going to go to a quick little simulation here which might help illustrate that idea. So what we're going to do here is we're going to create a wave here. And when we create this wave, I'm going to change this a little bit. I'm going to change this frequency. I'm going to restart this puppy. But I'm going to change the frequency down to, let's see. Let's change it down to 0.25 hertz. Okay? So basically, if it's at 0.25 hertz, okay, then it's going to be at, there's going to be one vibration every 4 seconds. But I'm going to slow-mo this puppy a little bit. If I can kind of get there. Let's see. There we go. Okay. So I'm going to start a wave here. It's going to oscillate. And as we see here, what's going to happen is it's going to vibrate back. It's a fixed end, so it's going to vibrate back on the opposite side here. But what we're going to generate here is areas where this is going to be an area of destructive interference. This right here in the middle is going to be an area of constructive interference. Now, you're not going to see it as much here with this right here, but this is what's going to be described as the fundamental frequency. This is the lowest frequency that can create a standing wave on the string. And we're going to presume, for argument's sake, that this string is fixed on both ends. And what we're going to see here is that we're going to get a high amplitude in the middle. That's going to be where areas of constructive interference, where the wave that's reflected is going to meet the wave coming here, and those wave crests are going to match up. And those are going to help reinforce each other. But what I'm going to do here is I'm going to double this frequency to 0.5 hertz. And now when you do that, you're going to see that what's going to happen here, let's restart this puppy. Change that to 0.5 hertz. And now we're going to actually generate, I'll speed it up a little bit. We're going to see that you're actually going to generate two standing waves here, if this is the case. We get two crests, and this middle is going to represent an area where it destructively interferes. I'm going to triple this frequency. And if that's the case, let's go back one here. I'm going to triple this frequency, and now you're going to see that we're actually going to end up with 3 standing waves that are going to be generated in this string here. Okay? And so let's look at kind of the math behind why this happens. So when we have this standing wave, there's 2 terms you need to understand. One of these is areas where we are going to get constructive interference, where they're going to help reinforce each other. We're going to call those antinodes, I should say. Those are going to be the areas of maximum displacement from the equilibrium. The areas that do not seem to vibrate at all, we're going to describe those as being the nodes. Okay? So in this case, I would have 1, 2, 3 nodes, and I'd have 1, 2 antinodes. Okay? So let's build upon this idea. Let's go down here and let's kind of cover this up a little bit. Better to conceal than reveal. Okay, so what we've got here is, this is the basic lowest frequency that we can get. This is the fundamental frequency. Now, when you look at it, one thing that's going to be a little confusing is trying to determine the wavelength. But you have to imagine that a wave is going to go like so, and it's fixed at this end, but you have to presume that this wave would kind of extend off into across here. So at this fundamental frequency, this length between this node and this node is actually 1/2 of the entire wavelength. This wave would go like so to create one entire wave. So in reality, my wavelength, my lambda for this, is actually 2 times this length L. This entire wavelength is 2L. Now the frequency at this level is going to be the velocity of this wave divided by 2 times the length. Because remember, velocity equals frequency times lambda, times my wavelength. So if I want my frequency by itself and my wavelength is 2L, I'm going to take velocity divided by 2L. We're going to call that F sub 0, which is going to be my fundamental frequency. This is what I would describe as being my first harmonic. Now the next time I can get a standing wave is going to be if I double that frequency. My frequency is twice as much. Okay, my frequency is twice as much. That means my wavelength is going to be half as much. So instead of it being 2L, I'm going to take 2L and divide it by 2. This is going to be my second harmonic. Now in this case, now you can see that my wavelength is where it was 2L here. Now my entire wave traverses this distance. That is one length here, okay? So my wavelength here is technically just L. If that's the case, my frequency is twice as much. And here you should recognize that I've got 1, 2, 3 nodes and 1, 2 antinodes. In the first situation with my fundamental harmonic, I have 1, 2 nodes and just 1 antinode right there. Let's keep going. My third harmonic right here is going to have 3 times the frequency. So what I'm going to do there is take my initial fundamental wavelength of 2L and divide it by 3 to get my wavelength. So you can actually see here that my wavelength is actually 2/3 L. This is the length of one wave here. And in this case, I'm going to have 1, 2, 3, 4 nodes and 1, 2, 3 antinodes. You can probably figure out where we're going from here. There's a rhythm, there's a pattern that's emerging here. All I'm doing is taking this fundamental wavelength and dividing it by the harmonic in each case to figure out what that fundamental wavelength, or to figure out what the wavelength is for each harmonic. Each time, I'm just going up with my frequency. Now I've quadrupled the frequency. Now my wavelength is going to be 1/4 of what it was before. This is actually the length of one wave. I've quadrupled my frequency. My wavelength here is actually 1/2 L. Again, in this case, 1, 2, 3, 4, 5 nodes, 1, 2, 3, 4 antinodes. And we can keep going on in perpetuity here. We can just kind of keep layering higher and higher harmonics on top of this. Now let me show you how this actually works. I'm sure just diagrams and simulation doesn't quite seem to sink in. I can show you how this really works in back. Just give me a second. So I have in back an oscillator. Right now it's vibrating at 82.5 hertz. And what I've got is this string attached right here. It's fixed at 2 ends. Now I've got a meter stick right here. And this wavelength right now, or this distance from this node to this node, is actually 1.3 meters, which means that my fundamental wavelength is actually 2.6 meters because that's 2 times that length. Okay? Now, I want to find a case where I can get a standing wave here for this little set of string here. So I'm going to change this frequency, and as I do this, you're going to see that we're actually going to have situations where this is going to end up vibrating, but we want it vibrating right here. You can tell that this is going to be a fundamental frequency. It's fixed at this end, it's fixed at this end, and this happens to be vibrating at 22.3 hertz. So what I'm going to do here is I'm going to take this 22.3 hertz,
and I'm going to multiply it times 2.6. And I'm going to find out that this ends up being a wave speed of 58 meters per second. Now that wave speed is going to be the same all the way down here. And so what I can do here is I can take this. I know that wave speed is always going to be 58 meters per second on that string. Remember, the wave speed can be calculated if you understand what the density is of this string in terms of its mass, and also what the weight of that string is in terms of its, in terms of its tension, how tight it is, okay? So what I can do with each of these is figure out what frequency is going to work by simply taking my velocity and dividing it by my fundamental frequency here. So if I take 58 and divide it by 1.3 meters, because 1.3 meters is going to be half of my first wavelength, I'm going to find out that it ends up being 44.6 hertz. So let's see what happens when I change this to 44.6 hertz. I'm going to adjust this. I'm going to ramp this up. 44.6 hertz, and you're going to see at that level, now we actually get 2 standing waves in this string. Okay? I've got a node, I've got another node, and I've got another node, I've got an antinode, I have an antinode. Okay? What's the next harmonic going to be? Well, we're going to take 58, we're going to divide it by 0.87. I'm going to find out that my next harmonic here should be at 66.7 hertz. So we're going to change this, 66.7 hertz. There we go. And so now you're going to see that we actually have 3 antinodes, and we're going to have 4 nodes. If I want my next one, it's going to be 58 divided by 0.65, because that's going to be my wavelength. That's 2L divided by 4. So I'd expect my next fundamental harmonic to be my next harmonic to be at 89.2 hertz. Let's give that a try. And so now you should be able to see here I've got one antinode, a second node, another antinode, a node, another antinode, a node, and an antinode and a node. So you can see here that the math kind of works for this. When we've got a string fixed at both ends, I can figure out what the wavelengths are and what the frequencies are, as long as I know what the velocity of the wave is on that string. So let's look at a couple demo problems with this. So let's say you're playing the guitar. The E string on a guitar measures 64 centimeters, has a fundamental frequency of 329 hertz. When the string is placed against the second fret, now you hear an F sharp that has a frequency of 370 hertz. The frequency has increased, the wavelength is shortened because I've shortened that string there, so my nodes are a little bit closer together. How much shorter is the string? Well, the first thing you're going to have to do is take what the problem is giving you. If that is my fundamental frequency and the length of that string is 0.64 meters, this is where it's tricky. That means that my fundamental wavelength is actually twice this length. That's 1.28 meters. My unknown, okay, my velocity of that wave, I've got to figure that out first. 329 hertz times 1.28 meters. That means that that wave is traveling along that guitar string at 421 meters per second. Remember, that's based in part on the weight of that guitar string and how tightly it's stretched. So if that's the case, now my frequency, when I've got my finger on that second fret, is 370 hertz. That is going to be my new wavelength, but remember, my wavelength is 2 times that L, that length of the string. I'm calculating 1.14 meters, which means that my actual L is only 0.57 meters. I have moved this guitar string 7 meters shorter because I started with that string being 64 centimeters long. Now let's incorporate that idea of the tension and the weight. So let's say I've got a 1 meter steel wire. It's got a mass density of 2.00 times 10 to the negative third kilograms per meter. Remember, that is my value for mu. That's going to be that linear mass density of that string. It's under a tension of 150 newtons. What is the fundamental frequency of this wire? So here are some things that this problem is giving you. The length between these two nodes is 1 meter. I know that my fundamental frequency is 2L, so my fundamental wavelength is going to be 2 meters. My mu is 2.00 times 10 to the negative third kilograms per meter. And so what is my fundamental harmonic going to be on this string? If you recall earlier, we had this equation for my velocity, that the velocity of a wave on string is going to equal the force of tension divided by my mu. I know that for my fundamental frequency, I'm going to take my wavelength of that fundamental frequency, and that's going to be 2L. So now let's start crunching in the numbers. My tension in that wire is 150 newtons. My linear mass density is 2 times 10 to the negative third kilograms per meter. I know that this wire is 1 meter long, so the fundamental wavelength is going to be 2 meters. I'm going to find out that this wire will vibrate at 120 hertz. So, you've got an assignment and a short lab for next time. Make sure you complete those. Until then, happy trails.
Who cares about the clouds when we're together? Just sing a song and think about sunny weather. Happy trails to you. Till we meet.